Hey, welcome to The Explainer. Today, we're going to dive deep into something you feel every single day, but probably don't think too much about: heat. We are going to unpack the really elegant, simple science that connects everything from a hot day at the beach to the energy that's literally locked inside chemical bonds. So, let's get into it. So, have you ever thought about this? It's a total kitchen mystery, right? You've got aluminum foil and a baked potato in the same oven at the exact same temperature. So why is one perfectly fine to touch while the other would give you a nasty burn? Well, the very same science explains how a firefighter suit works and why the ocean can feel so cool even when the beach sand is hot enough to burn your feet. All right, so here's our game plan. We're going to start with that firefighter and the beach to figure out a really key property of matter. Then we'll see how scientists actually measure this stuff, look at which way energy is flowing, and finally, learn the language that chemists use to talk about it all. Okay, first stop. We're on the hunt for the one single property that ties all of these random-seeming examples together. And it turns out it all comes down to a really simple idea: how much a substance kinda likes to hold on to heat. Now, the official sciencey term for this is specific heat capacity, but really, you can just think of it as a substance's thirst for heat. See, something with a high specific heat capacity is super thirsty. It can just drink up tons and tons of heat energy without its own temperature really changing that much. But something with a low value, it gets full on heat really fast, and its temperature just skyrockets. Okay, and this is where it all clicks. Just look at these numbers. Water, which is, what a potato is mostly made of, has a massive specific heat capacity, 4.18. It holds on to a ton of energy. But look at aluminum foil. Its value is way down at 0.9. That means it heats up fast, yeah, but it also loses that heat almost instantly. That's why you can touch it. And there's our beach sand, with a low value of 0.835, which is exactly why it gets so incredibly hot under the sun. In fact, water's capacity is more than 5 times that of sand. It literally takes over 5 times the energy to raise the temperature of water by just 1 degree compared to sand. And that is precisely why a huge lake or the ocean can stay so refreshingly cool way into the summer, long after the ground all around it is baking hot. So we know what this property is now, but how does a scientist actually measure it? I mean, how do you trap and count something as slippery as heat? Well, the trick is to create a perfectly isolated little world. Which brings us to our next section. The technique is called calorimetry, and the gadget they use is a calorimeter. The whole point here is to build an isolated system where you can measure every little bit of energy that's changing inside without letting any of it escape out into the room. And you know what's cool? It doesn't have to be some $1,000,000 machine. You can actually make a surprisingly good calorimeter with just 2 styrofoam coffee cups, one stuck inside the other, with a lid and a thermometer. This setup is amazing at trapping heat, so you can watch exactly what happens to the water inside. That water is going to tell us the whole story. And the experiment itself is beautifully simple. First, you start with an amount of water that you've already measured, at a temperature you already know. Then, you introduce the change. Maybe you drop in a hot piece of metal, or maybe you mix in a chemical to start a reaction. After that, you just watch the thermometer. The change in the water's temperature, that tells you everything you need to know. And all that data you just collected gets plugged into this one super important equation. Q is the heat energy that was moved around. You figure it out by taking the mass of the water, M, times its specific heat capacity, C, which we already know, times the change in temperature you just measured, delta T. This little formula is the key to actually putting a number on heat. Okay, so now we can measure the amount of heat. But what about its direction? Because in any change, whether it's physical or chemical, energy is either flowing out of the thing you're studying and into the world around it, or it's being pulled in from the world around it. Chemists have a formal name for this energy flow: enthalpy change, and they write it as delta H. Now here's the really convenient part. In a simple setup like our coffee cup, where the pressure isn't changing, this enthalpy change, this delta H, is the exact same thing as the heat flow, Q, that we just learned how to calculate. Pretty handy, right? So this energy flow can go one of 2 ways. If a reaction releases energy, we call it exothermic. Just think exo for exit. The stuff around it, like the water in our cup, gets hotter, and we say the delta H value is negative. If a reaction absorbs energy, we call it endothermic. Think endo for enter. The surroundings get colder, and the delta H value is positive. That sign tells you everything about the direction. So, here's the bottom line. It all comes back to that simple thermometer in our coffee cup. If the water temperature goes up, it means heat was released by the reaction. It's exothermic. If the water temperature goes down, it means heat was sucked in by the reaction. It's endothermic. Simple as that. All right, we've totally got the concepts down. So for our last step, let's look at how chemists actually write all this stuff down. There's a clear, efficient language they use in what are called thermochemical equations. So let's take the creation of water, which is a very exothermic reaction. There are basically two standard ways to write this. First, you can literally include the energy as if it's a product of the reaction. Or you can write the equation normally and then just state the delta H value next to it. Just notice, for an exothermic reaction, that delta H value is negative. Both of these notations mean the exact same thing. But, sometimes a picture is worth 1,000 words, or maybe 1,000 joules. So chemists also use these really simple graphs called potential energy diagrams to show the whole energy change in just one glance. And these diagrams make the whole idea crystal clear. For an exothermic reaction, the ingredients, the reactants, start out at a high energy level. Then the reaction happens, and the products end up at a lower energy level. Energy was released, so the arrow points down. For an endothermic reaction, it's the total opposite. The system has to absorb energy, so the reactants start low and have to climb up to a higher energy product. The arrow points up. It's that easy to read. So let's do a super quick recap of what we covered. Specific heat capacity. That's what explains why some things get hotter than others. We measure that heat flow using calorimetry. The overall energy change is called enthalpy or delta H. And that energy can either flow out in an exothermic reaction or flow in during an endothermic one. Think about it. From the instant cold pack you use for a sprain, that's an endothermic process sucking heat from your skin, to the roaring exothermic reaction of a campfire that keeps you warm. This transfer of energy is happening all around us, all the time. Now that you actually know the language and the science behind it, where are you going to see it next? Thanks for watching.